Hello there. Welcome to the Dozing Explorer.
I'm so glad you found your way here tonight.
I am here to be your quiet guide on a gentle journey, adrift through the universe of wonder, designed to help you unwind, to relax, and to find your way to a deep and restful sleep. There is nothing you need to learn, nothing to remember. All that is asked of you is to settle in, to close your eyes, and to allow your mind to drift, to float on the sound of my voice as we explore the quietest and most fascinating corners of existence. Your only task is to rest. Tonight, we are going to drift into one of the most profound and ethereal concepts in all of physics. We are not going to study it, but rather we will simply wander through its strange and silent corridors. We are going to explore the world of antimatter. It is not a place, but a reflection, a perfect and elusive mirror to the universe we know. It is the silent twin of every particle that makes up you and me and the stars. It is a substance of pure light, of perfect balance, born in the first fiery moment of creation and whispering its secrets from the heart of distant galaxies and even from within the gentle curve of a simple piece of fruit. It is the echo of reality, a concept so vast it holds the answer to why we are here at all. This journey is a passive one. It is a gentle cognitive load, a series of fascinating, low-stakes wonders designed to give your mind just enough to hold on to keep it from wandering into the worries of the day, and to instead guide it softly toward the shores of sleep. And just before we begin our exploration, if you find that these quiet wanderings help you unwind, if they bring you a sense of peace or calm, please consider subscribing to the channel. It is a simple, silent gesture that helps other sleepy souls and other dozing explorers find their way here to this quiet harbor too. But for now, all of that is far away. There is nothing left for you to do today. You have done enough. You can let go of all your thoughts, all your plans for tomorrow.
Let them dissolve.
Your only job now is to breathe, to feel the weight of your body settling in, growing heavy, feeling supported and safe. Give yourself permission to let go completely. Settle in, breathe deeply, and let our journey into the silent, shimmering world of antimatter begin. At the very beginning of our universe, in the first fleeting moment after the Big Bang, the cosmos was filled with a brilliant, chaotic ocean of pure energy. This energy, in its infinite power, did something magical. It condensed, cooling just enough to crystallize into substance. But it did not just create the matter that we know. For every single particle it forged, every electron, every proton, it also created a perfect, identical twin with an opposite charge. This twin is antimatter. Imagine a sculptor carving a statue from stone. Where the statue exists, a matching empty space is also created. In the dawn of time, the universe created both the particle and its antiparticle, a perfect symmetrical balance of positive and negative, a universe and its perfect, silent reflection. The most fundamental and poetic property of antimatter is what happens when it finally meets its counterpart. When a particle of matter, like an electron, touches its antimatter twin, the positron, they do not collide in a violent way. Instead, they simply cease to be. The two particles, the real and the reflection, embrace and are both instantly and completely converted back into the pure energy from which they were born. This process is called annihilation. It is a perfect transformation, a return to light, releasing two tiny flashes of energy, two gamma-ray photons that speed away in opposite directions, a final, silent testament to the perfect balance that has been restored. It is nature's most efficient recycling, turning all of its substance back into pure, radiant light without any loss. The first hint of this mirror world came not from a powerful telescope, but from the mind of a quiet physicist named Paul Dirac in 1928. He was working on an equation to describe the behavior of the electron, a fundamental piece of our world. But his equation, elegant and profound, yielded two possible answers. One solution described the electron perfectly, but the other described something strange, a particle with the exact same mass as the electron, but with a positive charge instead of a negative one. At first, this was thought to be a mathematical curiosity, a ghost in the machine. But Dirac trusted his mathematics and bravely proposed that this particle must be real. He had, on paper, discovered antimatter. Only 4 years after Paul Dirac predicted its existence, the anti-electron was found in the real world. In 1932, a physicist named Carl David Anderson was high in the mountains, studying the mysterious cosmic rays that constantly rain down upon our planet from deep space. He used a device called a cloud chamber, which allows us to see the faint, misty trails left by invisible particles. As he watched, he saw a track curve through the chamber's magnetic field. It curved with the exact same grace and weight as an electron, but it curved in the completely opposite direction. It was the unmistakable signature of a particle with a positive charge. He had captured the first photograph of Dirac's ghost. He named this new particle the positron. You do not need to travel to a distant galaxy or a high-energy laboratory to find antimatter. In fact, you likely have a source of it resting in your kitchen right now. A simple, humble banana is a natural, albeit tiny, producer of antimatter. Bananas are rich in potassium, and a very small fraction of all potassium is a naturally radioactive isotope called potassium-40. As this isotope slowly and harmlessly decays over time, it will, on occasion, undergo a process that emits a single positron, an anti-electron. On average, a typical banana will release one of these antimatter particles about every 75 minutes. This tiny speck of the mirror world appears, travels a microscopic distance, and then, upon meeting an electron in the fruit, vanishes in a tiny, imperceptible flash of light. The universe is a place of profound symmetry, and the creation of matter is no exception. Just as matter and antimatter can annihilate to become pure energy, the reverse is also true. This process is called pair production. If a photon of light, such as a high-energy gamma ray, possesses enough energy and passes close to the nucleus of an atom, that burst of light can simply disappear, and in its place, a pair of particles will spring into existence, an electron and its antimatter twin, the positron.
Energy in this beautiful transformation becomes substance.
It is a constant reminder that the light that fills the cosmos and the matter that forms our world are two sides of the same fundamental coin, interchangeable and eternal. The greatest mystery surrounding antimatter is not what it is, but where it is. According to our best understanding of the Big Bang, that initial burst of creation should have produced matter and antimatter in perfectly equal amounts. But if that were true in the cooling moments of the infant universe, every particle would have found its antiparticle, and everything would have annihilated into a vast, empty cosmos filled with nothing but light. We would not be here. The stars, the planets, and our bodies would not exist, yet we do. This profound puzzle, known as baryon asymmetry, suggests that for perhaps every billion particle-antiparticle pairs, a single extra particle of matter was somehow created, a tiny rounding error in creation's ledger that tipped the balance and allowed our entire universe to survive. Scientists have wondered if perhaps the antimatter is simply
Somewhere else.
Could there be vast regions of space, perhaps entire galaxies, made not of matter but of antimatter? An anti-galaxy would look identical to our own. It would have anti-stars, shining with the same light, orbited by anti-planets, which might even have anti-water and anti-life. From a distance, it would be indistinguishable from a matter galaxy. But if such a galaxy existed and were to drift too close to a matter galaxy like our own Milky Way, the boundary between them would be the most violent place in the universe. A colossal, shimmering wall of annihilation, releasing an unimaginable torrent of gamma rays. We have searched the skies for this signature, and so far we have found nothing, suggesting our observable universe truly is made of matter alone. Because antimatter annihilates on contact with any matter at all, even the air, it is the most difficult substance in the universe to store. You cannot hold it in a bottle or a box. To study it, scientists at facilities like CERN in Europe must use an incredible invention called a penning trap. This device holds charged antiparticles, like antiprotons, in a near-perfect vacuum. It then uses a powerful combination of electric and magnetic fields to create an invisible magnetic cage. The antiparticles are suspended, levitating in the absolute center of the trap, held perfectly still by these fields, never allowed to touch the walls of their container, where they would instantly vanish in a flash of light. The anti-electron, or positron, has a remarkable and life-saving use in modern medicine. You may have heard of a PET scan, which stands for positron emission tomography. In this procedure, a patient is given a special tracing dye containing a harmless radioactive sugar. As this sugar travels through the body, it decays and releases positrons, the very same antimatter particles discovered in cosmic rays. These positrons travel only a millimeter or two before they encounter an electron in the body's tissue. They annihilate, releasing 2 gamma rays that fly off in perfectly opposite directions. A ring of sensitive detectors around the patient captures these rays, tracing them back to their exact point of origin, creating a detailed map of metabolic activity deep within the brain or body. Just as our world is built from electrons and protons, the mirror world is built from positrons and antiprotons. An antiproton is the twin of a proton. It has the exact same mass, but where the proton has a positive charge, the antiproton has a negative one. In 1995, scientists at CERN achieved a monumental milestone. They took these 2 mirror world ingredients, the negative antiproton and the positive positron, and for the first time, gently guided them together. The positron began to orbit the antiproton just as an electron orbits a proton. They had created the first ever complete atom of antimatter, antihydrogen. It was a perfect, stable and complete reflection of the simplest atom in our own universe. Antimatter is, without question, the most expensive and valuable substance ever conceived. It is not valuable because it is rare, but because it is so colossally difficult to create and maintain. The process requires immense particle accelerators, colossal magnets, and an unfathomable amount of energy. In 1999, NASA scientists performed a calculation and estimated that to produce a single gram of antihydrogen, an amount smaller than a jelly bean, it would cost approximately $62.5 trillion. The total amount of antimatter that all of humanity has ever created in all of our experiments, if gathered together, would be less than a grain of sand and would vanish in a blink if it touched the ground. For a long time, there was a profound question that puzzled physicists. Does antimatter fall down or does it fall up? Our best theories, including Einstein's, predicted it should behave just like normal matter, obeying the same gravity. But no one had ever been able to test it. An antimatter particle is so light and its electrical charge is so strong that its behavior is completely dominated by stray magnetic fields, making it impossible to see the tiny pull of gravity. It was a mystery that seemed almost impossible to solve, leaving a small, tantalizing possibility that antimatter might be the source of a hypothetical anti-gravity that pushed things away. Recently, an incredibly precise experiment at CERN known as Alpha-G finally answered the ancient question of how antimatter interacts with gravity. Scientists managed to create and trap small, neutral clouds of antihydrogen atoms. By trapping them in a special magnetic bottle and then very, very slowly weakening the magnetic fields at the top and bottom, they could watch where the anti-atoms drifted as they escaped. After countless observations, the result was conclusive. The antihydrogen atoms were pulled downward toward the Earth, in precisely the same way as regular hydrogen atoms.
Antimatter does not fall up.
It falls down just as we do, bound by the same gentle, universal laws of gravity that hold the galaxies together. Even particles that have no charge at all have an antimatter twin. The neutron, which sits with the proton in the nucleus of an atom, is electrically neutral. Its antimatter partner, the antineutron, is therefore also neutral. So how are they different? The difference lies one layer deeper. Neutrons are made of smaller particles called quarks.
An antineutron is made of the corresponding antiquarks.
While the total charge adds up to 0 in both cases, the internal arrangement is a perfect mirror image. Furthermore, while the neutron is neutral, it acts like a tiny magnet with a north and south pole. The antineutron also acts like a tiny magnet, but its polarity is flipped, a perfect magnetic reflection. Before an electron and a positron annihilate, they can sometimes be drawn together by their opposite charges and briefly enter into a delicate, swirling dance. They can form a fleeting and exotic atom called positronium. It is an unstable, phantom-like structure where the electron and the positron orbit each other, a tiny solar system bound not by gravity but by electrical attraction. This strange atom, made of only a particle and its antiparticle, cannot last. In less than a microsecond, the two partners spiral inward, their dance ends, and they annihilate, dissolving together back into pure gamma-ray light. It is one of the most short-lived and simplest atomic systems in the known universe. Beyond the bananas in our kitchens, our entire planet is constantly being showered with tiny amounts of natural antimatter from space. High-energy particles called cosmic rays, forged in distant supernovas and other cosmic engines, perpetually slam into the upper layers of our atmosphere. When these incredibly fast particles strike the nucleus of an air molecule, the sheer energy of the impact creates a cascade, a shower of new particles that rains down toward the Earth. Within this shower are fleeting positrons and antiprotons. These antiparticles are born in the sky above us every moment of every day, only to be caught and annihilated by the dense sea of regular matter that is our atmosphere. Using the European Space Agency's Integral satellite, which is designed to see high-energy gamma rays, astronomers have made a breathtaking discovery. They found a vast, mysterious cloud of antimatter surrounding the supermassive black hole at the center of our own Milky Way galaxy. This cloud is enormous, stretching thousands of light years across, and it is composed almost entirely of positrons. The sheer scale of it is staggering, implying that something at the galactic core is producing antimatter at a tremendous rate. Scientists are still unsure of the exact source. It could be annihilating dark matter or perhaps jets of energy from the black hole itself. But it is a silent reminder that the mirror world exists on a galactic scale. The fundamental reason that antimatter is so incredibly energetic is that its annihilation is a process of perfect efficiency. When we burn fuel like wood or gasoline, we are only harvesting a tiny fraction of the energy stored in its chemical bonds. Even in a nuclear reaction, only a small percentage of the atom's mass is converted into energy. But in matter-antimatter annihilation, 100% of the mass of both particles is converted directly into pure energy. Following Einstein's famous equation,
E=mc², this makes it pound for pound
the most potent and powerful energy source theoretically possible in the universe, releasing thousands of times more energy than a nuclear reaction of the same mass. Because of its incredible energy density, antimatter has been the fuel of choice for countless science fiction stories, powering the starships that journey between galaxies. While we are nowhere near producing the quantities needed to power a real starship, the science is sound. A tiny amount, perhaps only a few grams, less than a handful of sugar, could theoretically produce enough energy to propel a spacecraft on an interstellar journey. The challenge lies not just in producing it, but in harnessing it. The annihilation releases gamma rays, which are incredibly difficult to capture and direct. But it remains a tantalizing, if distant, dream for future explorers. Tool. When Carl Anderson first saw the track of the positron in his cloud chamber, he was not entirely certain what he had found. The particle curved with the mass of an electron, but the charge of a proton. Was it a new particle or a regular electron that was somehow
traveling backward in time?
This idea, as strange as it sounds, was actually one interpretation of Dirac's original equation. The mathematics suggested that an antiparticle was indistinguishable from its regular particle traveling in reverse. While physicists today prefer the antiparticle model, this strange, poetic idea still lingers, suggesting time itself is a two-way street, even if we can only perceive one direction. The profound mystery of why our universe is made of matter at all is a puzzle that scientists are still desperately trying to solve. In 1967, the physicist Andrei Sakharov proposed that three conditions must have been met in the early universe for this imbalance to occur. First, the universe must have been out of thermal equilibrium. Second, a fundamental law that is normally symmetrical must have been broken. And third, there must have been a way to create more protons than antiprotons, a process that to this day has never been observed. These Sakharov conditions form the blueprint for our search, a map that might one day lead us to the origin of our own existence, hidden in the first second of time. 23. While a Penning trap works perfectly for charged antiparticles, it is useless for an atom of antihydrogen. Because the antihydrogen atom is neutral, its negative antiproton and positive positron balance each other out, it does not feel the pull of the trap's electric fields. To hold these neutral antiatoms, scientists had to invent an even more complex device called an IOF trap. This trap uses an incredibly complex arrangement of magnetic fields, creating a magnetic bowl. The antiatom is like a tiny, weak magnet itself, and it is naturally drawn to the point of the weakest magnetic field which the trap creates in its very center. It is held in place like a marble settling at the bottom of a bowl, a truly delicate and wondrous feat of engineering. The particles that make up the nucleus of an atom, protons and neutrons, are known collectively as baryons. The great mystery of our existence is therefore called the baryon asymmetry problem. The question is simple. Where did all the antibaryons go? The imbalance that allowed us to exist was infinitesimally small. For every 1 billion antibaryons, it is believed there was 1 billion and 1 baryons. All the pairs annihilated, leaving behind that tiny 1 in a billion remainder. That remainder, that cosmic leftover, is what forms every galaxy, every star, every planet, and every single atom in your body. We are the survivors of a perfect ancient war, built from the fortunate few that were left behind. In that first hot, dense soup of the early universe, particles and antiparticles were not only annihilating, they were also being constantly created. The cosmos was so energetic that photons of light had enough power to spontaneously burst into matter-antimatter pairs, a process we call pair production. For a time, the universe was a seething, shimmering equilibrium, with matter and light flashing back and forth, particles being born from light and dying back into it an instant later. It was only as the universe expanded and cooled that the photons lost the energy needed to create new pairs. The annihilations continued, but the creation stopped, and the great winnowing of matter began, leaving only the tiny surplus behind. The antiproton, the mirror twin of the proton, is not a simple, single particle. Just as the proton is made of 3 smaller particles called quarks, the antiproton is made of 3 antiquarks. These antiquarks have the same mass as their quark counterparts, but again, all their charges and quantum numbers are reversed. The antiproton is a stable particle, just like the proton. If left alone in a perfect vacuum, an antiproton would, in theory, exist forever. It is only its environment, our universe made of overwhelming matter, that makes it seem fleeting. In a mirror universe, it would be the proton that would be the exotic, fleeting particle, vanishing the moment it appeared. Physicists at CERN have learned to become masters of this mirror world, manipulating these exotic particles with incredible precision. To make antihydrogen, they must first create and capture clouds of antiprotons. They then must create and capture a separate cloud of positrons. Then, in the most delicate step of all, they must very, very gently push these two clouds together, allowing them to mix at incredibly low temperatures. If they mix too hot, they will just bounce off each other. But if they are cold enough, the slow-moving antiproton can gently capture a passing positron, which will settle into orbit around it, forming a neutral antihydrogen atom, a tiny, man-made speck of the anti-world. Now, one of the key properties of annihilation is that it always conserves the momentum of the particles. When an electron and a positron, both nearly at rest, meet and annihilate, they vanish. But their mass energy cannot just disappear. It must go somewhere. It erupts into two photons of light, or gamma rays. To conserve momentum, these two photons fly off in perfectly opposite directions. It is this precise 180-degree signature that allows a PET scanner to work. By detecting two photons arriving at the exact same time on opposite sides of the detector ring, the machine knows with certainty that an annihilation has occurred, and it can draw a perfect line between those 2 points, pinpointing the exact location of the event deep inside the body. The concept of antimatter forced physicists to reconsider the nature of the vacuum. We tend to think of empty space as just that, empty. But the laws of quantum physics suggest something far stranger. A vacuum is not empty, but is instead a seething, bubbling foam of virtual particles. For incredibly brief moments, a particle and its antiparticle can spontaneously borrow energy from the vacuum to spring into existence. They exist for a fraction of a second, a virtual pair, before they must pay back the energy and annihilate each other, vanishing back into the foam. This means that empty space is actually a chaotic dance of matter and antimatter, being born and dying in timescales too fast for us to see. 130, while the anti-hydrogen gravity experiment at CERN was a monumental success, it was also unimaginably difficult. The force of gravity is bafflingly weak, the weakest of all the fundamental forces. An anti-hydrogen atom's neutral charge means it is not affected by electric fields, but it still behaves like a tiny magnet. The Earth's own magnetic field, and even the tiny magnetic fields from nearby electronic equipment, could pull on the anti-atom with more force than gravity. The scientists had to create a region of space so perfectly shielded, so magnetically silent, that the faint, whispering pull of the entire planet Earth could finally be measured on a single, isolated anti-atom. Seen when a proton and an antiproton annihilate, the process is far more complex than the simple electron-positron dance. A proton and antiproton are not fundamental particles. They are composed of quarks and antiquarks. When they collide, it is this complex bundle of ingredients that annihilates, exploding into a shower of smaller, fleeting, and exotic particles called pions and muons, which then quickly decay into other things like neutrinos and gamma rays. It is a much more intricate and dazzling display of physics, a tiny, momentary echo of the particle cascades that happen in the upper atmosphere when a cosmic ray strikes. We are kept safe from the antimatter in cosmic rays by our planet's magnetic field. This field, which makes our compasses point north, also acts as a colossal, invisible shield. When charged particles from space, including positrons and antiprotons, stream toward Earth, they encounter this magnetic field and are deflected. They are guided into vast, looping spirals, trapped in belts of radiation high above the atmosphere, known as the Van Allen belts. This protective magnetic bubble channels the most dangerous radiation away from the surface, allowing life to flourish below, largely untouched by the tiny, constant rain of the mirror world from deep space. Scientists have managed to measure the properties of antimatter with astonishing precision, and every test has confirmed that it truly is a perfect mirror. They have measured the mass of the antiproton and found it to be identical to the proton's mass. They have measured the charge of the positron and found it to be the exact opposite of the electrons. They have even used lasers to study the antihydrogen atom, watching how it absorbs and emits light. They found that it responds to the exact same colors, the same frequencies of light, as a regular hydrogen atom. Every property, every law of physics appears to be perfectly, beautifully symmetrical. So this perfect symmetry is precisely what makes the greatest mystery so much deeper. If matter and antimatter are truly identical in every way except for their charge, then there is no known law of physics that should have preferred one over the other during the Big Bang. The universe, it seems, should not be able to choose. This leads scientists to hunt for a tiny, subtle difference, a crack in the mirror. They are searching for a new physical law, something not yet discovered, that might have treated matter and antimatter just slightly differently in the first fiery moments of creation, giving matter the tiny, crucial advantage it needed to survive. The decay of potassium-40 in a banana, which releases a positron, is a natural example of a force known as the weak nuclear force. This force is responsible for certain types of radioactive decay. In this process, a proton inside the potassium nucleus is not stable, and it spontaneously transforms into a neutron. To conserve the electric charge, this transformation must release a particle with a positive charge. That particle is the positron, the anti-electron. A neutrino is also released, and the two particles fly out of the nucleus, and the element itself changes. It is a quiet, slow, and constant process of transformation, a form of alchemy happening in nature, powered by the weak force. 36. The idea of antimatter seems to belong to the realm of the exotic, but the first person to propose it, Paul Dirac, was known for his love of simplicity and mathematical beauty. He believed that the laws of nature must be fundamentally elegant. His equation, which so beautifully described the electron, was a combination of Einstein's special relativity and the new world of quantum mechanics. He was so confident in the elegance of his own mathematics that when it produced the extra solution, the positron, he accepted it as a truth about nature long before it was ever seen. A true testament to the power of a beautiful idea to predict a hidden part of reality. When an antiproton, with its negative charge, is first introduced to a cloud of positrons, with their positive charge, the two are naturally drawn together. But they are often moving too fast. They will fly past each other or spiral around and fling each other away. The great challenge in making antihydrogen is to make the particles cold, which in physics just means making them move very, very slowly. Scientists use a technique called laser cooling to slow the positrons, and magnetic cooling for the antiprotons, chilling them to just a few degrees above absolute zero. Only in this state of profound stillness can the two gentle moving particles finally find each other and combine. While we have never found an anti-galaxy, there is a possibility that there could be anti-stars floating within our own. A star made of antimatter, an anti-star, would generate light in the exact same way as a normal star, through the fusion of antihydrogen into antihelium. It would shine just as brightly. It would be completely invisible to us, a perfect disguise. The only way to spot it would be if it happened to drift through a cloud of interstellar gas. The resulting annihilations would produce a unique and powerful gamma-ray signature. Astronomers are actively searching for this faint signal, hunting for a single, hidden mirror star within our own cosmic neighborhood. The amount of energy released in an annihilation is so total that it is difficult to comprehend. If you were to take a single paperclip and a matching paperclip made of antimatter and touch them together, the resulting release of energy would be more than 10 times greater than the explosion of the most powerful nuclear weapon ever detonated. It is an energy scale that dwarfs all of our conventional sources. This is why it is so treasured in science fiction, and why it is so difficult to manage in reality. Even the annihilation of a few anti-atoms in a trap at CERN is a detectable event, a tiny, pure flash of energy in a world of matter. The puzzle of the universe's survival, the baryon asymmetry, may have been solved by an unimaginably heavy and fleeting particle. Some theories propose that in the very early universe, there existed another particle, a heavy Majorana neutrino. This particle would have had the unique property of being its own antiparticle. As the universe cooled, these particles would have decayed, but they might have decayed in an asymmetrical way, producing just slightly more matter than antimatter. This hypothetical particle, if it existed, would have been the thumb on the scale, the subtle imbalance that allowed the cosmos to be born from a sea of light. The positron, the antimatter twin of the electron, is a stable particle. Just like an electron, if left completely on its own in a perfect vacuum, it would never decay. It would exist forever. Its seemingly short life is not a property of the particle itself, but a property of the universe it finds itself in. It is like a single perfect snowflake landing in a warm ocean. The snowflake is stable, but its environment is not. The moment the positron is created, it is surrounded by a vast, overwhelming sea of electrons, and its eventual annihilation is all but instantaneous. In a universe made of antimatter, it would be the electron that would be the fleeting, exotic visitor. 2. To create the antiprotons needed for their experiments, scientists at CERN use a massive machine called a particle decelerator. First, they use a different accelerator to slam a beam of high-energy protons into a block of solid metal, like copper. The sheer force of this impact, this focused burst of energy, creates a shower of new particles, and among them, a precious few antiprotons. These antiprotons are born traveling at nearly the speed of light. They must then be captured, separated from all the other debris, and decelerated or slowed down in a series of magnetic rings over and over again, until they are moving slowly enough to be caught and held in a trap. Don't we think of our bodies as being made purely of matter? But this is not entirely true. Just like a banana, our bodies contain a tiny amount of naturally occurring potassium-40. This means that every human being is also a very, very faint source of antimatter. As you are lying here, settling into sleep, your own body, over the course of many hours, will naturally produce several positrons from these tiny, harmless radioactive decays. These anti-electrons appear, travel a microscopic distance, and then annihilate with a nearby electron, releasing a flash of light too small to see. You are, in a very small but very real way, connected to the mirror world. The cloud of antimatter at the center of our galaxy is a genuine puzzle. It is so large and is producing so many gamma rays from annihilation that astronomers are struggling to explain it. The annihilation rate suggests that thousands of billions of tons of positrons are being destroyed there every single second. This is far more than known sources like supernovas or pulsars seem able to produce. This has opened the door to more exotic theories, with some scientists proposing that this colossal cloud could be the first visible sign of dark matter, suggesting that when dark matter particles collide, they might be annihilating and producing the positrons we can see. But the very first antiparticle, the positron, was discovered in 1932, but it took much longer to find the antiproton. The reason is mass. An antiproton is almost 2,000 times heavier than a positron. To create one, you need to concentrate almost 2,000 times more energy into a single point. This was beyond the reach of cosmic rays or early experiments. It was not until 1955 at the Bevatron Particle Accelerator in California that physicists finally had a machine powerful enough to focus the required energy. They slammed protons together with enough force to create the first artificial antiprotons. confirming that the mirror symmetry of nature applied not just to light particles, but to the heavy building blocks of atoms as well. The idea of antimatter seems to violate our common sense, but the universe is built on a foundation of these beautiful symmetries. Physicists have found that for every property of a particle, there is a corresponding conservation law. There is a symmetry for electric charge, for momentum, and for energy. Paul Dirac's discovery was that the universe also seems to have a deep symmetry between matter and antimatter. The equations that govern reality simply do not seem to have a preference for one over the other. They are a balanced set of rules, a perfect mirror, and our matter-filled existence seems to be the one profound exception to this perfect balance. When you receive a PET scan, the radio tracer you are given is a marvel of chemistry. Scientists take a simple, essential molecule like glucose or sugar, which the body's cells naturally consume for energy. They then attach a radioactive isotope to it, one that they know will decay and release positrons. When this tagged sugar is injected, the body's most active cells, such as busy brain cells or, unfortunately, rapidly growing cancer cells, will consume more of it. As the sugar concentrates in these active areas, the attached isotope releases its positrons, and that part of the body begins to light up with annihilation signals, giving doctors a map of the body's inner function. Could a universe made of antimatter support life? All of our evidence says yes, absolutely. An anti-hydrogen atom behaves identically to a hydrogen atom, just with its charges flipped. It would bond with anti-oxygen to form anti-water. This anti-water would be chemically identical to our water. It would freeze at the same temperature and boil at the same temperature. Anti-carbon atoms would form the same complex chains, creating the building blocks for anti-DNA and anti-proteins. An entire mirror biology is perfectly possible. A person made of antimatter would look and feel exactly like us, and they would likely be wondering in their own universe if a strange substance called matter could possibly exist. The total amount of anti-hydrogen ever created at CERN is vanishingly small, measured in just thousands of atoms. Even with all of our technology, we are not creating substance so much as we are coaxing it into existence, one anti-atom at a time. The amount of energy required to run the accelerators to produce these particles is billions of times greater than the energy we would get back from annihilating them. This is why antimatter is not a practical energy source for us right now. It is not something we can harvest. It is something we must build particle by particle at a truly astronomical cost. 50. This profound, perfect symmetry between the two worlds, matter and its mirror, is known in physics as CPT symmetry. It stands for charge, parity, and time. It states that if you were to take a particle, swap its charge for its opposite, charge, reverse its coordinates in a mirror, parity, and have it travel backward in time, it would be completely indistinguishable from its antiparticle. This is the deepest symmetry known in physics, a fundamental rule that seems to be written into the fabric of reality itself. It is the mathematical law that guarantees that the mirror world, even if we cannot see it, is as real and as valid as our own. The positron, or anti-electron, is not just a scientific curiosity. It is a tool used in industry to study the hidden flaws in materials. This technique is called positron annihilation spectroscopy. A beam of low-energy positrons is fired at a sample of metal or a semiconductor. These positrons travel into the material and, if the material is perfect, they will quickly find an electron and annihilate. But if the material has a tiny, microscopic flaw, such as a missing atom, a tiny crack, or a void, the positrons tend to become trapped in this empty space. They live just a fraction of a second longer in this defect before they annihilate. By measuring the tiny delay in the gamma rays, or their slight change in energy, scientists can detect these flaws with a sensitivity far beyond what a microscope can see, peering into the hidden, empty spaces of solid matter. When Paul Dirac first formulated his equation in 1928, the known particles were simple: the positive proton and the negative electron. His equation's prediction of a positive electron, or positron, was so strange that he was initially hesitant to publish it. He even wondered if the proton itself might be the particle his equation predicted, but that was impossible, as the proton is vastly heavier than the electron. He was forced by the sheer elegance and power of his mathematics to accept a radical new idea, that for every particle there must exist an antiparticle. He had discovered an entirely new symmetry of nature, a fundamental law, not by observation, but by trusting the profound beauty of a single mathematical formula. The most powerful thunderstorms on Earth can act as colossal natural particle accelerators, creating antimatter high above our heads. As powerful updrafts and downdrafts in a storm cloud separate electrical charges, they can build up an electrical field billions of times stronger than the one in our homes. This field becomes so powerful that it can accelerate stray electrons to near the speed of light. When these ultra-fast electrons slam into air molecules, they can trigger a cascade, including high net energy gamma rays. These gamma rays, in turn, can spontaneously convert into electron-positron pairs. For a fleeting moment, a bolt of lightning or a strong storm cloud can generate a terrestrial gamma ray flash, a brief, invisible burst that showers the sky with newly born antimatter. While we have created antihydrogen, the next great challenge is to create something more complex, like antihelium. An antihelium nucleus would consist of 2 antiprotons and 2 antineutrons orbited by 2 positrons. This is vastly more difficult to create. In 2011, an experiment at Brookhaven National Laboratory succeeded in smashing gold ions together at nearly the speed of light. In the chaotic fireball of this collision, among the trillions of particles created, they detected the unmistakable signature of a few antihelium-4 nuclei. These anti-atoms were stable, existing for a fraction of a second before they struck the detectors. It was the heaviest, most complex piece of the mirror world ever created on Earth. So one of the most delicate experiments at CERN is designed to measure the color of antihydrogen. Every atom, when excited by a laser, will only absorb very specific, precise frequencies or colors of light. This is its spectral signature, a unique fingerprint that reveals its internal energy levels. According to our theories, antihydrogen should have the exact same spectral fingerprint as regular hydrogen. Scientists have managed to trap a few anti-atoms and shine a precisely tuned laser on them. They found that the antihydrogen atoms did indeed respond to the exact same frequency of light, absorbing it and becoming excited just as a normal hydrogen atom would. It was another beautiful confirmation that the mirror world is a perfect reflection of our own. The idea that a positron is an electron traveling backward in time was championed by the physicist Richard Feynman. He developed a way to visualize particle interactions using simple drawings, now called Feynman diagrams. In these diagrams, a positron moving forward in time is drawn as the exact same line as an electron moving backward in time. To the mathematics, they are identical. This interpretation offers a strange and beautiful perspective on annihilation. When an electron meets a positron, it is not 2 particles colliding. Instead, it can be seen as a single electron traveling along, which at a certain point in time suddenly reverses its own direction in time and begins to travel backward, appearing to us as a positron. When an electron and a positron meet and form that fleeting atom called positronium, it can exist in 2 different states. If the 2 particles are spinning in opposite directions, it is called para-positronium. It is incredibly unstable and will annihilate almost instantly, in a fraction of a nanosecond, into 2 gamma rays. But if the particles are spinning in the same direction, it is called orthopositronium. This state is slightly more stable. It cannot decay into 2 photons and must instead decay into 3. This process is slower, allowing the orthopositronium to survive for a whole 142 nanoseconds, a lifetime that is 1,000 times longer, a fleeting eternity for this exotic, ghostly atom. In 1995, when scientists at CERN first created those 9 atoms of antihydrogen, they were not able to trap them. The anti-atoms were created hot, meaning they were traveling very fast. They flew out from the point of creation, and in less than 40 nanoseconds, they traveled 10 meters across the chamber and struck the walls of the detector. Upon impact, they instantly annihilated. The scientists did not see the antihydrogen itself. They detected its death, the sudden characteristic burst of energy from the antiproton annihilating with a proton in the wall, a clear and unmistakable signature that for a fleeting moment, a complete atom from the mirror universe had existed. There is a fundamental particle, a ghost-like traveler called the neutrino. It has almost no mass and no charge, and it streams through planets and people as if they were not there. For a long time, it was assumed that the neutrino, like the photon, might be its own antiparticle. However, we now know that there is also an antineutrino.
They are distinct.
The neutrino is always left-handed, spinning like a left-handed corkscrew as it flies, while the antineutrino is always right-handed. This perfect, mirror-like separation in their spin is one of the most profound and curious asymmetries in the known laws of physics, a deep clue that the universe does indeed have a preferred handedness. The anti-world is not just a concept, it has its own version of the periodic table. Antihydrogen with 1 antiproton is the mirror of hydrogen. Antihelium with 2 is the mirror of helium. It is theoretically possible to have anticarbon made of 6 antiprotons, 6 antineutrons, and 6 positrons. This anticarbon would behave chemically just like our carbon. It would form long antipolymer chains, anti-graphite, and even anti-diamonds. Every single element we know has a theoretical antimatter counterpart, and if a place existed where this antimatter could survive, it would build a world just as complex, just as varied, and just as beautiful as our own. While antimatter seems to be gone from our universe, there is a tiny, lingering imbalance that we can observe. In the decay of some exotic particles called K-mesons, scientists have observed a subtle but undeniable violation of the mirror symmetry. If you watch these particles decay and then watch their antiparticle counterparts decay, the two processes do not happen at the exact same rate. The mirror is slightly warped. This discovery, made in 1964, was the first proof that the laws of physics are not perfectly symmetrical. It is this tiny, known crack in the mirror, this CP violation, that physicists believe is the key to understanding the original, grand imbalance that allowed matter to survive at the dawn of time. The Penning trap, the magnetic bottle used to hold antiprotons, is a device of incredible precision. It must hold its captured particles in a vacuum so perfect it is billions of times emptier than the vacuum of outer space. If even a few stray molecules of air were to leak in, the antiprotons would instantly annihilate and the experiment would be lost. This ultra-high vacuum ensures that the antiprotons can be held, suspended in their magnetic cage, for days, weeks, or even months at a time, allowing scientists the long, quiet periods they need to gently study their properties, one particle at a time. 63. The concept of annihilation as the ultimate power source presents a profound paradox. It is the most efficient fuel possible, but it is also the most inefficient to create. The energy required to make one antiproton is billions of times greater than the energy you get back from annihilating it. This is because particle accelerators are not precise tools. They are brute force instruments. They smash particles together, and the antiproton is just one tiny, rare piece of shrapnel that emerges from a vast explosion of other, useless debris. It is like trying to build a single watch by smashing two locomotives together and then searching for the one perfect gear that emerges from the wreckage. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, we see a universe that is almost perfectly uniform in temperature. This tells us that in the beginning, everything was in a state of thermal equilibrium, a perfect, smooth soup. But as the physicist Andrei Sakharov pointed out, this very equilibrium is a problem. If the universe was in a perfect, stable balance, no reaction should have been favored over another. The creation of matter and antimatter should have been perfectly equal. To create the imbalance we see today, the universe must have passed through a period of violent, rapid change, a sudden cooling or expansion that threw it out of balance, allowing the laws of physics to choose a side, favoring matter just slightly. See the vast, mysterious cloud of antimatter at the center of our galaxy, detected by its gamma-ray glow, is shaped like a giant distorted fountain. It is not a perfect sphere, but is instead elongated, with one lobe stretching far above the galactic plane and another, smaller lobe below it. This strange shape has led some astronomers to theorize that it might be the remnant of a jet fired from our supermassive black hole, Sagittarius A case, sometime in the distant past. It is possible that as material fell into the black hole, it was superheated and blasted back out into space in two powerful, focused beams, and this high-energy process was, and perhaps still is, a colossal factory for producing positrons. With the antineutron, the neutral twin of the neutron is a particularly elusive particle. Because it has no charge, it cannot be held in a magnetic penning trap, and because it is a single particle, it cannot be held in the Ioff trap designed for neutral antiatoms. Antineutrons are, for this reason, almost impossible to capture. They can only be studied in the fleeting moment after their creation, before they drift away and strike a piece of matter. When an antiproton annihilates on a proton or neutron, it will sometimes release an antineutron in the debris. Scientists can detect this by seeing it fly a certain distance and then suddenly annihilate on another nucleus, a two-step signature that reveals the ghost-like particle's brief journey. The radioactive isotope potassium-40, which we find in bananas, is a primordial part of our planet. It was forged inside a massive star billions of years ago. That star exploded in a supernova, scattering its newly created elements, including that potassium, across space. This dust cloud eventually coalesced to form our solar system, our planet, and everything on it, including the first life. The fact that a banana, or your own body, can produce an antimatter particle is a direct and unbroken link to the fiery heart of a long-dead star. The positrons released are a tiny, harmless echo of the cosmic violence that was necessary to create the atoms that make our quiet existence possible. If an antiproton and an electron, two particles that are not counterparts, were to meet, they would not annihilate. The antiproton is the mirror of the proton, not the electron. Instead, the negative antiproton and the negative electron would simply repel each other, pushing each other away with their like charges. An antiproton can only annihilate with a proton. An electron can only annihilate with a positron. This specificity is the key to the mirror world. Each particle has only one perfect partner. It is a lock-and-key mechanism on a fundamental scale, ensuring that the universe maintains its distinct realms of matter and antimatter. The handedness of the neutrino, its left-handed spin, and the right-handedness of the antineutrino is a violation of a symmetry known as parity. Parity is the idea that the laws of physics should be the same for an experiment and for its mirror image. In the 1950s, the physicist Chien-Shiung Wu conducted a brilliant experiment showing that this is not true for the weak nuclear force. She observed radioactive decay and proved that the universe is not ambidextrous. It can tell the difference between left and right. This discovery was a profound shock, proving that the mirror of reality is not quite perfect, a crucial clue in the quest to understand our own existence. When scientists at CERN succeeded in making anti-atoms cold enough to trap, it was a breakthrough years in the making. The anti-atoms are formed at temperatures of thousands of degrees. To cool them, they are held in their magnetic trap and mixed with a cloud of ultra-cold positrons, which have already been cooled using other methods. The hot anti-atoms collide with the cold positrons, transferring their heat like a hot spoon being placed in a cup of cold water. This process, called sympathetic cooling, slowly chills the anti-hydrogen atoms until they are moving slowly enough to just half a degree above absolute zero that the shallow magnetic trap can hold on to them, preventing their escape. When the particle detectors at places like CERN are some of the most complex machines ever built, essentially colossal three-dimensional digital cameras. The size of a multi-story building, they are built in layers, with each layer designed to detect a different type of particle. The inner layers track the curved paths of charged particles. The next layers measure their energy. The outer layers are designed to catch particles like muons, which can pass through feet of solid metal. When an annihilation occurs, the shower of resulting particles flies out in all directions, and the detector captures a snapshot of this event, allowing scientists to meticulously reconstruct the moment of impact, identifying every piece of the debris to confirm that antimatter was truly there. While we have confirmed antimatter falls down, the precision of that experiment is still being improved. Scientists want to know if it falls down at the exact same rate as normal matter. Einstein's theory of general relativity, our theory of gravity, is built on a principle called the weak equivalence principle, which states that gravity must pull on all mass and all energy in the exact same way. If it were discovered that antimatter falls just 1% slower or 1% faster than normal matter, it would be the first ever violation of this principle. It would mean Einstein's theory is incomplete and would open a doorway to a completely new understanding of gravity itself. The simple positron has a powerful, if destructive, application in astrophysics. Some types of supernovas, or exploding stars, are thought to be triggered by an avalanche of pair production. In a very massive dying star, the core becomes so hot that its own light, its gamma rays, becomes incredibly energetic. This light spontaneously starts to convert into electron-positron pairs. This process robs the star's core of its energy, the very pressure that was holding the star up against its own colossal gravity. This pressure suddenly vanishes, and the star's outer layers collapse catastrophically inward, triggering a runaway thermonuclear explosion that tears the entire star apart. Richard Feynman's idea of a positron being an electron moving backward in time solves a curious puzzle of creation. When a photon of light becomes an electron-positron pair, how does one particle know it must be the electron and the other the positron? In Feynman's view, there is only one particle. The photon, a packet of energy, simply strikes the particle's timeline and knocks it, forcing it to reverse its direction in time. What we see as a photon vanishing and two particles appearing is, in this view, just a single particle interacting with light at one specific moment, its timeline bending back upon itself, creating the illusion of a pair where there is only one. So the Penning trap, which holds antiprotons, uses a combination of two fields. A very strong magnetic field, aligned vertically, forces the particles to travel in tight little circles.
This keeps them from flying out to the sides.
At the same time, a weaker electric field acts like a cap on the top and bottom of the trap. This electric field pushes the negatively charged antiprotons back toward the middle, preventing them from escaping vertically. The antiprotons end up trapped in a tiny, dense cloud in the very center, spiraling in tight circles while also bouncing gently back and forth between the electric caps, perfectly suspended in a void. The decay of a positronium atom is a perfect, tiny laboratory for testing our most fundamental theories. Because the atom is made of only two simple particles, an electron and a positron, its properties can be calculated with astonishing precision. Physicists can predict exactly how long it should live and exactly what the energy of its decay photons should be. They can then create positronium in the lab and measure these properties. These experiments are a high-stakes test. If the measurements ever disagreed with the predictions, even by a tiny amount, it would mean our entire understanding of quantum electrodynamics, the theory of light and matter, is incomplete. So far, the theory has passed every test perfectly. 78. While we have confirmed antimatter falls down, the precision of that experiment is still being improved. Scientists want to know if it falls down at the exact same rate as normal matter. Einstein's theory of general relativity, our theory of gravity, is built on a principle called the weak equivalence principle, which states that gravity must pull on all mass and all energy in the exact same way. If it were discovered that antimatter falls just 1% slower or 1% faster than normal matter, it would be the first ever violation of this principle. It would mean Einstein's theory is incomplete and would open a doorway to a completely new understanding of gravity itself. The mirror world of antimatter raises a profound philosophical question. Is there any absolute way to define positive and negative charge? We simply call the charge on an electron negative by convention, a label we assign to it. If our universe were made of antimatter, the anti-inhabitants would surely call the charge on their electron, the positron, negative, because that is what their science would be built upon. From their perspective, our particles would be the strange ones with the anti-charges. This suggests that these labels are relative and that the universe only cares about the perfect symmetry. The fact that there are two, and only two, opposite sides to the coin of electric charge. The antimatter shower from a thunderstorm is not just a small, fleeting curiosity. In 2009, a research aircraft deliberately flew into a thunderstorm to study its gamma rays. It was unexpectedly struck by a brief, intense burst of particles. When they analyzed the data, they realized the plane had flown directly through a cloud of positrons, an antimatter beam that had been generated by the storm just moments before. This beam of antimatter was surprisingly intense, a powerful and previously unknown atmospheric phenomenon. It is a stunning reminder that the laws of high-energy physics are not confined to distant stars or giant labs, but are actively at play in the sky above us. But one of the most ambitious antimatter experiments at CERN is called GBAR, which stands for Gravitational Behavior of Antihydrogen at Rest. Its goal is to create an anti-ion. First, it creates an antihydrogen atom. Then it tries to add a second positron to it. This would create an antihydrogen ion with a positive charge. The reason for this complex step is that a charged ion is much easier to trap and manipulate than a neutral atom. The experiment's ultimate plan is to trap this single anti-ion, cool it to a state of near absolute stillness, and then gently strip away the extra positron, allowing the now neutral anti-atom to fall in a vacuum, a new and incredibly precise way to watch gravity's effect on the mirror world. The fact that we are made of baryons, protons and neutrons, is a key part of the great asymmetry puzzle. But there is another family of particles called leptons, which includes the electron. The universe also has a profound surplus of leptons. For every electron, there is no positron to be found. This means that the great imbalance at the dawn of time happened in both families. The universe not only made more baryons than anti-baryons, but it also made more leptons than anti-leptons. Any true theory of our origin must explain both of these surpluses at the same time, showing how the scales were tipped in favor of both the building blocks of atomic nuclei and the particles that orbit them. When an anti-star is proposed as a candidate for dark matter, it is not as a single fundamental particle, but as a primordial black hole or a massive compact halo object, macho. The idea is that in the early universe, perhaps dense clumps of antimatter collapsed to form black holes or incredibly dense cool stars. These antimachos would be floating through our galaxy's halo, invisible to us. They would be dark and they would have gravity. We search for them by watching for microlensing events. If one of them passes in front of a distant star, its gravity will bend the star's light, acting like a lens and causing the star to briefly and suddenly brighten. The radioactive tracers used in PET scans have very short lives by design. They are created in a small medical particle accelerator called a cyclotron, which is often located in the hospital itself. The isotopes are made, quickly attached to the sugar molecules, and then injected into the patient, all within a matter of minutes. The most common isotope, fluorine-18, has a half-life of only 110 minutes. This means it decays very quickly, releasing its positrons and allowing the scan to be completed, and then it vanishes from the body, leaving no lingering radioactivity behind. It is a medical tool designed to disappear, its usefulness tied directly to how fleeting its existence is. The vacuum foam of virtual particles, the constant dance of matter and antimatter being born and dying in empty space, is not just a theory. It has real measurable effects. One effect is called the Casimir effect. If you take two perfectly smooth, uncharged metal plates and place them incredibly close together in a perfect vacuum, they will be pushed together by an unseen force. This force comes from the vacuum itself. The tiny space between the plates restricts the kinds of virtual particles that can pop into existence there, while the normal vacuum on the outside is still full of all kinds of virtual pairs. This imbalance in the vacuum foam creates a real physical pressure, pushing the plates together. The antiproton, being the mirror of the proton, is a composite particle. A proton is made of two up quarks and one down quark. The antiproton is therefore made of two anti-up antiquarks and one anti-down antiquark. The properties of these antiquarks are a perfect mirror. The up quark has a positive charge of 2/3, so the anti-up has a negative charge of 2/3. The down quark has a negative charge of 1/3, so the anti-down has a positive charge of 1/3. When you add these up, two anti-ups and one anti-down, you get a total charge of -1, a perfect composite mirror to the proton's positive one. 7. While anti-hydrogen has been studied with lasers, the precision is not yet as good as it is for normal hydrogen. The reason is the difficulty of the experiment. For normal hydrogen, scientists can have a bottle containing trillions of atoms all at room temperature and shine a laser through it. For anti-hydrogen, they have only a few dozen or perhaps a few hundred anti-atoms trapped in a complex magnetic cage and chilled to near absolute zero. Measuring the properties of this tiny, delicate, and fiercely guarded sample is one of the most technically demanding experiments ever devised, pushing the boundaries of what is possible in a laboratory. The annihilation of matter and antimatter does not always produce only two gamma rays. While that is the most common outcome for a slow-moving electron and positron, it is not the only one. If they are moving very fast, they can produce a single, very high-energy photon, or if they are in the orthopositronium state, they decay into 3 photons. If a proton and antiproton annihilate, they produce a whole spray of different particles. The only firm rules are that the fundamental laws must be conserved. The total energy must be the same before and after, the total momentum must be the same, and the total electric charge, which is 0, must also be conserved. Begin the 1960s, a physicist named Hannes Alf Venn proposed a cosmological model where the universe was, in fact, perfectly symmetrical. He suggested that vast cells of matter and antimatter existed, separated by invisible boundaries. He theorized that as these cells drifted and touched, the annihilations at the boundaries would push them apart, like foam bubbles on water, keeping them separate. This ambiplasma universe was an elegant idea, but it has not been supported by observation. We have never seen the gamma-ray signature of these vast boundaries, and the perfect smoothness of the cosmic microwave background suggests the early universe was a well-mixed soup, not a divided, cellular structure. NANTI, the anti-clicker for an antihydrogen atom, would be a device that emits antiphotons. But a photon, the particle of light, is one of the rare particles that is its own antiparticle. A photon and an antiphoton are the exact same thing. This is because the photon has no charge, no mass, and no other quantum number that can be flipped. It is a truly neutral and fundamental entity. This is why an antistar shines with the exact same light as a normal star. And it is why scientists can use a normal everyday laser made of normal photons to probe the inner workings of an anti-hydrogen atom. Light is the universal bridge, the common language between both worlds. 91. The search for a tiny difference between matter and antimatter is one of the highest priorities in all of physics. Scientists at CERN are running an experiment called EDGES, which is attempting to make a beam of anti-hydrogen atoms. The plan is to send this beam flying through a series of special gratings. The anti-atoms will be deflected by gravity as they fly. By measuring this deflection with extreme precision, they hope to compare the gravitational pull on anti-hydrogen to hydrogen. Even a 0.01% difference would be a revolutionary discovery, a Nobel Prize-winning glimpse into why the universe chose us over our mirror image. The mystery of our existence. The baryon asymmetry is a question of survival. In the first second of the universe, there was a war between creation and annihilation. For a brief time, the two forces were in balance, with light creating pairs as fast as pairs were annihilating back into light. But as the universe expanded and cooled, the photons lost the energy to create new pairs. The creation stopped, but the annihilations continued. In this great annihilation, almost all matter in the universe was destroyed, finding its counterpart and vanishing into a sea of radiation. We are, quite literally, the ashes of that fire, the 1 in a billion rounding error that was left over when the smoke cleared. The simple, humble banana is a wonderful, tangible link to these vast ideas. The fact that it contains potassium-40, which was forged in a supernova, is a reminder of our cosmic origin. The fact that this isotope decays, governed by the weak nuclear force, is a reminder of the fundamental forces that shape reality. And the fact that this decay on occasion releases a positron is a quiet, constant reminder that the mirror world, the world of antimatter, is not just a distant, theoretical concept. It is here now a real and natural part of our world, happening invisibly in the air we breathe and the food we eat, a silent, fleeting whisper of the universe's perfect symmetry. Positronium, the fleeting atom of an electron and a positron, is a fascinating toy for physicists. It is the lightest atom that can possibly exist. Because the two particles have the exact same mass, they do not orbit a central heavy nucleus like in a normal atom. Instead, they orbit each other, or more accurately, they orbit a common center of mass that is exactly halfway between them. They are locked in a perfectly balanced, swirling dance, a true partnership of equals, before they inevitably spiral together and vanish, their perfect symmetrical relationship ending as it began, in a flash of pure energetic light. So the handedness of the weak force, its preference for left over right, is a deep and troubling puzzle. Why should the universe care? Some physicists have proposed that this is a sign that we are only seeing half of the picture. Perhaps there exists a mirror weak force, one that we cannot feel, which is right-handed and interacts only with a hidden mirror set of particles. This would restore the universe's symmetry, but it would place it in a shadow world, a set of particles and forces that exist all around us but are completely invisible to us. A mirror sector of reality whose only hint is the lopsided nature of our own weak force. Cost of antimatter. The $62.5 trillion per gram is a number so large it is almost meaningless. It is perhaps easier to think of it in terms of time. The combined output of all the antimatter factories on Earth, like those at CERN and Fermilab, is measured in picograms or even femtograms per year. A picogram is a trillionth of a gram. At this rate of production, to create a single gram of antiprotons, the amount that would fit in a grain of rice, would take many billions of years, a time scale longer than the entire age of our solar system. It remains, for now, the most precious and unattainable substance in the universe. The idea of antimatter-powered starships, while distant, is not pure fantasy, and NASA has seriously studied the concept. The main challenge is propulsion. An antimatter engine would not be like a rocket we know. It would likely involve annihilating tiny pellets of antimatter with matter, releasing a flood of gamma rays. These gamma rays would be used to heat a propellant, like hydrogen, to unimaginable temperatures, creating a superpowered exhaust. Or more exotically, the gamma rays themselves could be focused by a gamma ray lens, which does not exist, or reflected by a sail to push the ship forward. It is a problem of engineering so profound that it borders on the magical. The discovery of the positron by Carl Anderson in 1932 was a triumph of experimental physics. He was using his cloud chamber to study cosmic rays, which are showers of particles from space. He placed a thick lead plate in the middle of his chamber. He saw a particle track enter from the bottom, curve through the magnetic field, pass through the lead plate, and then curve even more sharply on the other side. By seeing it slow down as it passed through the lead, he knew with absolute certainty the direction it was traveling. This proved it was a positively charged particle, but with the light, graceful curve of an electron. It was the first, undeniable physical proof of the anti-world. The deep mystery of baryon asymmetry is not just a question of the past. It is a question of the future. The proton, the building block of all matter, is thought to be an incredibly stable particle. But some theories that explain the original matter, antimatter imbalance, also predict that the proton must, eventually, decay. This decay would be fantastically rare, with a half-life of trillions upon trillions of years, far longer than the current age of the universe. Scientists are searching for this decay in massive, underground detectors, watching vast tanks of pure water, waiting for a single proton to suddenly vanish in a tiny flash of light. Finding it would confirm our theories of origin, but it would also mean that all matter in the deep, distant future will eventually dissolve. 100. The total amount of antimatter ever held in a trap at CERN, the anti-hydrogen atoms that were so painstakingly created, cooled and measured would, if all gathered together, be insufficient to even warm a cup of tea. Their importance is not in their energy, but in their mere existence. The fact that we can build, hold, and study a piece of the mirror world is one of the greatest scientific achievements in human history. It is a triumph of curiosity, a testament to our desire to understand the most fundamental rules of the cosmos, to hold in our hands a perfect, fleeting reflection of the substance that makes us, and to ask it the simple, profound question, why are we here and where did you go? 101. The experiments at CERN that study antimatter are models of patience and precision. In the experiment known as Alpha, which first trapped antihydrogen, the process is incredibly delicate. After creating and trapping the antiprotons and positrons in their separate wells, they are gently combined. In a typical experimental cycle, this may produce only a handful of antihydrogen atoms. The scientists must then hold these few anti-atoms, using their weak magnetic properties, for as long as possible. They have managed to hold them for over 15 minutes at a time, a truly heroic feat of engineering, allowing them to finally begin to study these elusive particles before they are lost. It is a form of physics built on capturing the most fragile, fleeting substance in existence, one atom at a time. Toot. One of the most profound tests of the mirror symmetry is the measurement of the antiproton's magnetic moment. All protons spin like a tiny top, and this spin creates a tiny magnetic field, just like a miniature bar magnet. The antiproton spins in the opposite way. Scientists at CERN managed to trap a single antiproton and measure its magnetic field with almost unimaginable precision. They found that its magnetic moment was identical to the proton's, just with the opposite polarity, a perfect mirror reflection. This test, one of the most precise comparisons between matter and antimatter ever performed, confirmed yet again that the symmetry between our world and its anti-world is perfect, making the mystery of our own survival even deeper. See, there is a specific particle, a type of B meson, that has become a crucial clue in the mystery of our existence. These heavy, unstable particles are created in accelerators, and they can decay in several different ways. In the 2000s, experiments at bee factories in California and Japan made a breakthrough discovery. They found that the B meson and its anti-B meson counterpart do not decay at the same rate. They found a small but clear difference in their behavior, a violation of the symmetry. This was only the second time such a crack in the mirror had been found, and it was a massive one. It proved that the laws of physics are not the same for matter and antimatter, providing the first strong experimental evidence for how a matter-dominated universe might have been possible. 117, when you see a cosmic ray detector, it is often a simple grid of sensors. When a particle from space, like an antiproton, strikes the top of the atmosphere, it creates a shower of secondary particles. This shower spreads out as it falls, like the spray from a hose. By the time it reaches the ground, it can cover an area as wide as a city. The detectors, spread out on the ground, will all click at the exact same millisecond. By comparing the precise arrival time at each different sensor, scientists can reconstruct the trajectory of the shower, tracing it back to a single point in the sky, and by analyzing the particles, they can determine what kind of cosmic ray, whether matter or antimatter, started it all. Key: the total charge of the observable universe appears to be, as best we can measure, exactly 0. For every proton with its positive charge, there is an electron with a negative charge. This perfect balance is a profound and beautiful symmetry. The early universe, in its particle-antiparticle soup, was also perfectly neutral. The symmetry between matter and antimatter was not just in amount, but in charge. The positron's positive charge balanced the electron's negative one, and the antiproton's negative charge balanced the proton's positive one. The fact that our universe, even after the antimatter vanished, remains perfectly neutral is a deep clue that whatever process saved the protons, it must also have saved an equal number of electrons. And the concept of a vacuum has changed completely because of antimatter. It is not an empty, passive stage. The quantum vacuum is a dynamic, active substance, a sea of potential. The laws of physics, combined with the uncertainty principle, allow particle-antiparticle pairs to be borrowed from this vacuum energy, existing for a fleeting moment before they must be repaid and vanish. A massive object like a black hole can warp this process. Near a black hole's event horizon, it is possible for a virtual pair to be created, and for one particle to fall in while the other escapes. This escaping particle becomes real, and it appears as a faint glow. Hawking radiation, a process by which a black hole can, over aeons, evaporate, its mass slowly turning back into particles, powered by the antimatter pairs in the quantum foam. TT. The term antimatter itself was coined in the 1930s, but it was not Paul Dirac who invented it. He simply called his particle the anti-electron. The word positron, which we use today, was suggested by his colleague Carl Anderson, who had actually found it. The more general and more poetic term antimatter grew in popularity as it captured the public's imagination. It perfectly described this new, profound idea of a mirror substance, a complete reflection of our world that seemed to belong more to philosophy or fantasy than to the rigorous mathematical world of physics. It is a name that still carries with it a sense of deep wonder and profound mystery. The energy released by annihilation is so vast, it is hard to scale down. We spoke of a paperclip, but let's consider something smaller. A single grain of sand and its anti-sand counterpart annihilating. The energy released would be roughly equal to the detonation of the atomic bomb dropped on Hiroshima. This is the power locked within E-MC2. It is the sheer, awesome efficiency of turning 100% of mass into pure energy. It is a reminder that the substance of our world, the quiet, stable matter we take for granted, is a form of crystallized, frozen energy on an unimaginable scale. And antimatter is the key that can unlock it. 2. The Eoff trap, which holds neutral anti-hydrogen atoms, is a marvel of weak force. It cannot grip the anti-atom tightly, as a penning trap grips a charged antiproton. It can only cradle it. The trap creates a magnetic dimple, a small region in space where the magnetic field is weakest. The anti-atom, being a tiny magnet, is naturally drawn to this calm spot, like a marble rolling to the bottom of a shallow bowl. But this bowl is incredibly shallow. The trap can only hold anti-atoms that are fantastically cold, moving at only a few miles per hour. A single energetic bounce would be enough to launch the anti-atom out of the trap, where it would be lost forever. Why is gravity so much weaker than the other forces? A simple refrigerator magnet can lift a paperclip, its tiny electromagnetic pull easily overpowering the gravitational pull of the entire planet Earth. This hierarchy problem is a massive puzzle. Some theories have proposed that perhaps gravity is strong, but it leaks into other hidden dimensions of space. We only feel a tiny fraction of its true strength. This is one of the reasons testing antimatter's gravity was so crucial. If it had behaved differently, it might have been a sign that it was interacting with these other dimensions, giving us our first tantalizing glimpse of a larger, hidden reality. 24. Could there be a fifth force of nature that we have not yet discovered? One that interacts differently with matter and antimatter? This is an active area of research. Physicists are constantly testing the laws of nature, looking for tiny deviations. They have tested the pull of gravity at very short distances and searched for new particles that might be carrying a new, undiscovered force, if such a force existed. And it pushed antimatter away while pulling matter, or vice versa. It could have been the driving mechanism for separating the two in the early universe, creating the vast, empty voids between galaxies as the two substances repelled each other. So far, no such force has been found. 5. The anti-alpha particle, the nucleus of anti-helium-4, which was created at Brookhaven, is the heaviest piece of antimatter ever made. It consists of 2 antiprotons and 2 antineutrons, all bound together by the strong nuclear force. Its discovery was a landmark, proving that the strong force, the glue of atomic nuclei, works in the exact same way for antimatter as it does for matter. It proves that the anti-periodic table is not just a theory. The anti-world can build complex, stable nuclei just as our world does. It is a confirmation that the laws of nuclear physics are also perfectly mirrored. In all of our observations, we have never seen an atom of matter spontaneously turn into an atom of antimatter. The laws of physics seem to forbid this. A proton, for example, has a baryon number of +1. An antiproton has a baryon number of 1. In all known interactions, this number must be conserved. You can create a proton-antiproton pair, total baryon number of +1 and 1.0, from pure energy, baryon number 0, but you cannot create a proton out of nothing. This conservation of baryons is the law that makes our universe stable, but it is also the very law that must have been broken just once, and just slightly, at the beginning of time. The most precise experiment in all of human history is the measurement of the electron's G factor, a property related to its magnetic moment. It has been measured to an accuracy of 1 part in a trillion. Scientists at CERN have been attempting to measure the same property for the positron. This is the ultimate test of the mirror. If those two numbers, for the electron and the positron, were to differ in the slightest, in the 10th or 11th decimal place, it would be a revolution. It would mean our most fundamental theory, quantum electrodynamics, is incomplete. As of now, within the staggering precision we can achieve, the two numbers are identical. The mirror is perfect. 28. When a cosmic ray, a high-energy proton from space, slams into the atmosphere, it can create a particle called a pion. This pion is unstable and quickly decays, producing another particle, a muon, and a neutrino. The muon is also unstable and it rains down on the Earth. In fact, several muons are passing through your hand right now. But if the original cosmic ray had been an anti-proton, it would have created an anti-pion, which would have decayed into an anti-muon and an anti-neutrino. We can detect these anti-muons at the surface. They are a constant, natural, and harmless stream of antimatter arriving on Earth, a steady messenger from the high-energy events in our galaxy. The AMS experiment, or alpha magnetic spectrometer, is a massive particle detector, much like the ones at CERN, but it is not on Earth. It is attached to the outside of the International Space Station. Its mission is to orbit the Earth and catch cosmic rays, including positrons and antiprotons, before they strike the atmosphere. By measuring their energy and direction, it is creating the most precise map ever of the antimatter that flies through our solar system. It is searching for a surplus of antimatter at certain energies, which could be the signature of annihilating dark matter. Or it could be looking for a single anti-helium nucleus, which would be the first ever proof that an anti-star exists somewhere in our galaxy. The sound of an annihilation, if we could hear it, would be silence. The event itself, the conversion of mass to energy, is instantaneous and does not produce a pressure wave, which is what our ears detect as sound. The explosion is a release of gamma rays, a form of light so energetic it is far beyond our ability to see. These gamma rays would then slam into the surrounding air, heating it and causing it to rapidly expand, which would create a shock wave, a thunderclap. So you would not hear the annihilation itself. You would hear the sudden, violent reaction of the air around it, the sound of normal matter being torn apart by the sudden, pure release of energy. 131. The energy in the annihilation of a single gram of antimatter is vast, roughly 90 trillion joules. This is enough energy to power an average car for over 30,000 years. It is enough to keep a bright light bulb lit for more than 10,000 years. It is an energy scale that is simply not human. It is the energy of stars and of the Big Bang. When we create a few anti-atoms in a lab, we are not harnessing this power. We are just holding a single, tiny spark from that original cosmic fire, a fire that consumed an entire universe and left only us, its ashes, behind. 32. When Paul Dirac's equation predicted the positron, it was a moment of profound unity in physics. It was the first time that Einstein's special relativity, the theory of high speeds, and quantum mechanics, the theory of the very small, had been successfully combined. The price of this combination was antimatter. The equation showed that if you try to describe a particle moving near the speed of light in a quantum way, you must include the possibility of its antiparticle. The anti-world is not an optional extra. It is a mathematical and logical necessity for the universe to be consistent with its own rules. If you were to fall into a black hole made of antimatter, the experience would be identical to falling into a regular one. The black hole itself is a region of space-time so warped that nothing, not even light, can escape. Its gravity is a property of its mass, and we know that antimatter has positive mass. You would be pulled by its gravity in the exact same way. You would cross the event horizon and be stretched by the tidal forces long before you ever reached the singularity of antimatter at its center. The fact that it was made of antimatter would be completely irrelevant to your journey, as the laws of gravity are the same for both worlds. The search for proton decay is one of the quietest and most patient experiments on Earth. In a massive, abandoned mine deep underground, shielded from cosmic rays by a mile of solid rock, sits a tank containing 50,000 tons of ultra-pure water. This tank is lined with thousands of the most sensitive light detectors ever made. The scientists are simply watching. They are waiting for one of the trillions upon trillions of protons in that water to spontaneously decay, an event which has never been seen. If it happens, it will release a tiny, characteristic flash of light. They have been watching for decades, and so far they have seen nothing. This tells us that the proton is stable for at least 10 trillion years, a testament to the profound stability of our world. What if the Big Bang was not the beginning? In one cosmological model, the universe bounces, it expands, then collapses back in on itself, and then bounces in a new Big Bang. Some theories have proposed that perhaps the universe switches its properties with each bounce. Maybe the previous universe was made of antimatter, and in the bounce that created our own, the laws of physics flipped, allowing matter to dominate this time. It is a grand, poetic, and untestable idea, but it speaks to our deep desire for symmetry, the feeling that the lost antimatter of our birth might not be lost at all, but might have simply had its turn, in a cosmos that existed before our own. So it's 6. The idea of antimatter has so deeply permeated our culture that it has become a staple of science fiction. It is the power source for the Starship Enterprise, a plot point in thrillers, and a symbol of ultimate power. But often it is depicted as a glowing, swirling, unstable energy. In reality, it would be stable, invisible, and look just like normal matter. Its only extraordinary property is its relationship with us. It is not inherently violent or chaotic. It is only its context, its existence in a universe that is its perfect opposite, that makes it the most volatile substance imaginable. It is a perfect mirror, and mirrors, when brought together, shatter. 37. The antimatter cloud at our galactic center is so diffuse that although it contains the mass of many suns, the particles are very far apart. A positron in this cloud might drift for 100,000 years before it finds an electron to annihilate with. This is why the glow is so steady. It is not a single, violent explosion, but a slow, constant, galactic-scale shimmer of annihilations, a fog of gamma rays built up over millions of years. It is the collective light from countless tiny, microscopic encounters between the world and its anti-world, playing out in the dark, vast spaces between the stars, a silent, ongoing song of mutual destruction. While a PET scan is a life-saving tool, it is also a source of radiation. The patient is injected with a radioactive material, and the annihilations produce high-energy gamma rays, which pass through the body. The dose, however, is very carefully controlled. It is designed to be as low as possible, comparable to the amount of natural background radiation we all receive from the Earth and from space over the course of a few years. It is a delicate balance, a trade-off where we accept a tiny, managed risk from the mirror world in exchange for the profound and life-saving ability to see the hidden inner workings of our own bodies. It's the anti-muon is a particle that rains down on us from cosmic ray showers. In 2001, an experiment at Brookhaven measured the magnetic moment of the muon and found a tiny discrepancy with our best theories. The muon seemed to be wobbling in a magnetic field slightly more than it should. This has led to a tantalizing possibility that the muon is interacting with a virtual particle that we have not yet discovered, perhaps from dark matter or another hidden force. Scientists are now repeating this experiment with incredible precision, and they are also planning to measure the anti-muon's wobble. If the anti-muon wobbles differently, it would be another profound crack in the mirror, a sign of new physics hiding just beyond our view. 40. The precision of the anti-hydrogen gravity experiment is staggering. The anti-atoms are released from their trap, and they fall a distance of only a few centimeters. But in that tiny drop, the scientists must account for the Earth's rotation. They must account for the tiny magnetic fields from the electrical equipment in the next room. They must even, in theory, account for the gravitational pull of the nearby Jura Mountains. The signal, the pull of the Earth, is so faint that it is buried under a mountain of noise. The experiment is a masterpiece of subtraction, of silencing the entire world so that the faintest, quietest whisper of gravity on a single anti-atom can finally be heard. The symmetry between matter and antimatter and its tiny violation is the answer to the oldest question, why is there something rather than nothing? If the universe had been born with a perfect, unbroken symmetry, it would have annihilated into a featureless, empty void of light. There would be no complexity, no stars, no life. Our existence is a privilege, a statistical anomaly. We are here because the mirror of reality, while beautiful, is not perfect. It has a tiny, subtle flaw, a 1 in a billion imperfection. And it is in that imperfection, that tiny crack, that our entire vast and wonderful universe was born. 2. The IOF trap that holds neutral anti-hydrogen is so shallow that the anti-atoms must be unimaginably cold. The temperature of a gas is just a measure of how fast its atoms are moving. Room temperature atoms move at hundreds of miles per hour. The anti-hydrogen atoms in the trap must be cooled to less than half a degree above absolute zero, the coldest possible temperature in the universe. At this temperature, the anti-atoms are moving at a literal crawl, at the speed of a slow walk. Only in this state of profound cryogenic stillness can the weak magnetic dimple of the trap hope to hold them, a delicate frozen piece of the anti-world. But the simple, everyday banana which we began with is a truly humble and profound object. It contains potassium forged in a star. It contains carbon, the basis of life. And as it sits, it quietly and harmlessly participates in the laws of the weak nuclear force, decaying and, on occasion, releasing a single positron.
A single particle of antimatter.
It is a tangible link, a bridge between the cosmic and the mundane. It is a reminder that the most exotic, vast, and powerful concepts in the universe are not just out there. They are also in here, part of our world, part of our food, and even part of our own bodies. The universe is not separate from us. We are a part of it. 144. The first anti-atom, anti-hydrogen, was made in 1995. The first heavy anti-nucleus, anti-helium-4, was made in 2011. The pace of this research is slow, careful, and incredibly difficult. Scientists are now dreaming of the next steps. Could we ever make anti-lithium or anti-carbon? Could we weld anti-atoms together to form anti-molecules? These are questions for the far future. Each step is exponentially harder than the last. For now, the focus remains on the simplest, most fundamental anti-atom of all, anti-hydrogen, as it still holds the deepest secrets, and its properties have yet to be fully explored. It is the Rosetta Stone of the mirror world. If an anti-star exists in our galaxy, the AMS detector on the space station is our best hope of finding it. It is searching for a single nucleus of anti-helium, A tiny bit of anti-helium can be created in cosmic ray collisions, but it is fantastically rare. If AMS were to detect a steady stream of anti-helium, or even a single nucleus of anti-carbon, it would be definitive proof. A cosmic ray collision cannot create something that complex. It would be the smoking gun, the undeniable evidence that somewhere in our own galaxy there is an anti-star, an entire factory of antimatter, steadily burning, fusing anti-hydrogen, and seeding the galaxy with the building blocks of a mirror world. To date, it has found none. 6. The anti-neutrino, the mirror twin of the neutrino, is a particle we are all familiar with, even if we do not know it. Nuclear reactors, which power our cities, are the most intense artificial source of antineutrinos on Earth. Inside the reactor core, the fission process creates unstable, heavy nuclei, which then decay. This decay process, governed by the weak force, releases a flood of antineutrinos. These ghost-like particles stream out of the reactor, passing effortlessly through the concrete shielding, through the Earth, and through our bodies. A constant, invisible and harmless reminder of the nuclear processes that power our world. The ultimate fate of antimatter research is not to build weapons or power starships. That is the realm of fiction. The true goal is to answer the simple, profound question of our own existence. We are a puzzle. The laws of physics as we know them say we should not be here.
And yet we are.
The only way to solve this puzzle is to study the missing part, the antimatter. By creating it, trapping it, and measuring it with exquisite precision, we are looking for the clue, the tiny difference that explains the imbalance. We are, in a very real sense, holding a mirror up to ourselves and searching for the flaw that allowed us to be real. The annihilation of an electron and a positron into 2 gamma rays is a perfect illustration of AM2. The m in that equation is the mass of both particles. The electron has a mass and the positron has an identical mass. When they annihilate, the total m is their combined mass, which is then converted into the total energy E of the 2 photons that fly apart. It is a perfect balanced equation. The substance of the 2 particles is not lost. It is simply translated perfectly and completely into the substance of light, a pure, energetic expression of their combined existence. The idea of a mirror world is a beautiful one. It implies a perfect symmetrical balance to all things. And in our most fundamental equations, this seems to be true. But the universe we inhabit, the one we can see and touch, is the exception. We are the result of a broken symmetry. This suggests a profound truth, that pure, perfect symmetry, while beautiful, is also sterile. A universe in perfect balance would be an empty universe. It is the imperfection, the flaw, the slight imbalance that allows for complexity, for structure, for change, and ultimately, for life. We are not an accident. We are the children of a fortunate imperfection. And so our quiet exploration of this mirror world, this perfect reflection of our own, draws to a gentle close. We have drifted from the first fiery moments of the Big Bang to the quiet, natural decays inside a simple banana. We have seen how this elusive substance is captured in vast, magnetic bottles and how it is used in the most delicate of medical procedures. We have wandered through the puzzle of our own existence, the 1 in a billion chance that allowed our matter world to survive. And we have found that this concept, which seems so alien, is not just a distant theory, but a fundamental part of the laws that govern our reality, a necessary and beautiful symmetry that defines what it means to be real. And so, our gentle drift through the silent, shimmering world of antimatter comes to a close for tonight. We have wandered the corridors of this mirror universe, not as students, but as passive observers, as dozing explorers. We have felt the deep, underlying symmetry of the cosmos, the perfect balance of particle and antiparticle, of creation and annihilation. We have touched upon the profound mystery of our own existence, the fortunate, tiny imbalance that allowed all of this. all of us, to be. We have seen how this echo of reality, born in the first flash of creation, is not just a distant, abstract idea, but is all around us. It is in the light from distant stars, in the invisible showers from our own atmosphere, and even in the quiet, microscopic processes within our own bodies. We are connected to this story. The iron in your blood, the calcium in your bones, the very atoms that make you, were forged in the same cosmic events that governed the Great War between matter and its mirror. You are a part of this story. You are a child of the asymmetry, a survivor of the Great Annihilation, a fortunate speck of matter imbued with the wondrous ability to contemplate the very laws that allowed it to exist. But those thoughts are for another time.
The journey is over.
All those vast cosmic ideas can now be allowed to dissolve. They can fade like gentle ripples on a still, dark lake. The only thing that matters now is your rest. Your mind has been gently held, and now it is time to let it go. There is nothing left to do, nothing to solve, nothing to hold on to. Your only task is to drift, to let the weight of your body feel heavy and safe and supported. You can let go of the day. You can let go of my voice, feel yourself floating in a quiet, dark and peaceful space. Let all tension melt away from your shoulders, from your mind, letting it all dissolve into the stillness. You are safe, and it is time for your well-deserved rest. Allow the gentle tide of sleep to pull you under. May your dreams be peaceful, and may your rest be deep. Good night.